In this video, we're going to talk about models, and this is a way to describe or explain physics or other scientific phenomena. So let's jump right in. So a model is a group of statements used to describe something, often used to define that thing. So if you thought about models as like physical objects, that is not what we're referring to when we call that a model. We're actually talking about is the statements or ideas that that model, that physical model, is depicting. So if you see like a model of a solar system where you've got the sun and then little planets around it, the idea that the sun is at the center of the solar system and planets move around it, that's the model that the physical object is depicting. So that's a nuanced difference, but I want to talk about it because we'll be doing some models later in the year that don't have a physical representation or don't have a diagram. They're just statements that explain something. So here's some examples. The atomic model is a bunch of statements saying here's what an atom is and here's how it works. The energy interaction model explains how energy does what energy does. It's a series of statements that we'll see later. The mechanical wave model is another model that we'll work with later this year that explains what is a mechanical wave, how does a mechanical wave act, and the mirror model is a model of saying here's how a mirror works, here's what a mirror does. So then the question is, why use models? And the answer is that simple definitions are usually insufficient to describe complex phenomena. So the basic definition of energy is often quoted as the capacity or ability to do work. But that doesn't actually explain anything. That doesn't have meaning. Yes, it accurately describes energy, but it's not useful for understanding why we care about energy. When we get to the energy model, you'll see there's a bunch of statements, and that explains what energy actually does, how it works, and that helps us to better understand the phenomena that we've given kind of the category of energy. Alternatively, some phenomena cannot be directly studied. We cannot, at this moment, actually figure out directly inside of an atom. Like we can't shrink ourselves down, get down inside of it, touch around, feel around, look at things, get out measuring tapes, etc. inside an atom. It's not possible because we don't have tools that small to actually do those measurements. Likewise, the sun or stars, we can't currently get anywhere, like we can't actually get close to the star, and we can't actually put anything inside the star to take measurements. So those are things we can't directly measure, but we can create a model. We can say, here's everything we observe, let's make some statements that would explain what we've observed. Models also promote an understanding of a concept. If we have a bunch of model statements, that helps us to then make predictions or to explain what's going on. This is a good example for a wave. You kind of intuitively probably know what a wave is. You could look at something and say, yes, that's a wave, or no, that's not. But once we have a model, it's easier to say, oh, I know why that is a wave, or I know why that's not a wave. Models can also be easily adapted to new evidence. If we see something new, we don't have to completely throw out our definition. We just add a new statement, or adjust an old statement, or tweak an old statement. It's sort of, if you want to think about it, it's a definition with lots of parts, so we can tinker with it as we need to. And then finally, this is the one that's most relevant or important for kind of your first few years of physics, if you continue on, is that some models simplify complex phenomena and make them more easy to work with. Because we don't always need the best depiction or most accurate description of something to actually care about what we're doing. We'll learn about kind of describing motion and using velocities and stuff like that in a couple weeks here. That is not technically correct or our most accurate description of kind of how things move. But the calculations that we would have to use are more involved, they're longer, they're more complex, they involve needing to know a lot more about math and the situation. But if we do those calculations and do the calculations we're going to do, we see that the numbers are 99.999999999% the same, because they're based on this one making some assumptions that are wrong, technically speaking, but not so wrong that they cause a problem. They're simplifying, and they're oversimplifying, some might say, what we're learning. So this is why models are also useful. Imagining atoms as little balls is great for chemistry, typically, because you can just imagine, okay, a bunch of atoms, a bunch of little balls stick together, and we get a molecule. That's totally fine if all you care about is the idea of a molecule being made up of atoms. It would be not worth it to try and imagine, okay, here's what the atoms actually are, and here's how they're connecting, if all you're trying to understand is molecules are made up of atoms. So that's our idea here behind models and why we use them.